Welcome back. So this is the last lecture for the first modulus of the course of molecular physics, and it's a part of the course that concerns the foundations of quantum mechanics. In the second part of the course, we shall instead look at the sort of specific application to first atomic and then molecular physics, providing the basis of the final project where the students will be requested to perform computer simulation of electronic structure. What we've been discussing quite broadly in the last several lectures are some Oxy approximation methods, which are useful to solve problems that otherwise could not be solved analytically, or in some cases, not even with the use of a computer. And, in particular, we discussed that, simple lattice discretization of the Hamiltonian and the space allows you to turn complicated problem, namely the solution of the eigenvalue problem with a differential operator, partial differential operator, such as the Hamiltonian, into a tractable matrix eigenvalue problem. However, we also discussed that typically the number of lattice points, and therefore the dimensionality of the space the one is mapping the problem onto, grows exponentially with the number of dimensions. Now, the number of dimensions is a concept that depends on the number of particles. I mean, clearly, we live, at least for the purpose of chemistry and all the applications we are concerned with in this course, we live in a three-dimensional vector, in a three-dimensional space. But when you have more than one particle, the number of coordinates you need to specify the system is number of dimensions times number of particles. So it's 3m. So as soon as you have a few particles, the effective dimension of your problem grows with the number of particles, and therefore the effective number of lattice points you need grows exponentially with the number of particles. For these reasons, methods based on discretizing space and then diagonalizing the Hamiltonian are doomed to fail as soon as you have a handful of particles. So in one of the previous lectures, we looked at an alternative solution which was based on expanding around a different, if you want, bases of eigenstates of the Hilbert space. You can think about lattice discretization as an expansion onto a specific base, the base of positions with given lattice discretized positions, with np is the number of points. So if you want, lattice discretization is basically a truncated basis expansion onto this specific base made of eigenstates of position operator. But in the previous lectures, we look at a more general expansion onto a general, sets of complete states, like truncated sets, which also leads to translate a differential operator H into a matrix. And therefore to an object that can be diagonalized. Obviously, the hope is that by judicious choice of this basis vector, you can sort of keep this number of points in the effective vector space as low as possible, thus extending the range of problems that can be tackled by this method. Notwithstanding all these nice features and hopes, and notwithstanding the fact that we could solve quite easily a problem that, we didn't know how to solve, like the double wall problem, there are many problems that cannot be tackled. Most of the problems of interest cannot be tackled even by this approach. And so what I will be telling you today is about one more There are many other different, approximations methods that have been developed, but many of them follow under, if you want, a family or a category of methods which share common features. And we refer to this as variational methods. Now, variational methods are really a family of methods, and we will encounter several of them in the second part of this course. But today I'm going to present rather the basic principle that is behind all of these methods, and that can be applied even to a very simple system, and perhaps we're going to spend some time trying to apply and see what it does. And the principle that I'm going to refer to is the very famous Ritz variational principle. Now, the Ritz variational principle is in fact a theorem that can be demonstrated. But that I will not be bothering you with the proof of. So I'm going to state it as a fact for the sake of this course. Just you should be aware of the fact that it is not just a principle, it is in fact a theorem. But let's not worry about this. And let's just say, what does this principle state? Okay, what does this theorem state? Okay, so suppose we have a Hamiltonian, and it's a well-known Hamiltonian. And suppose, so let's consider the ground state of this Hamiltonian. This is the ground state. Okay? Now, in most cases, I would not know what the ground state is, because if I knew, I would have solved the problem finding the ground state. Now, let's now consider any other state in the Hilbert space. Maybe it's an eigenvalue of the Hamiltonian. Maybe it's not even an eigenvalue of the state. Let psi be any, and I emphasize the total general character of this statement, any other point, any other element, or ray, if you want, of the same Hilbert space. Okay? Then, if I take the matrix elements of H with itself, which is, from the previous lectures, called the expectation value of the matrix element, and you, of course, normalize it, if the state is not normalized. Of course, if the state psi is normalized, you don't need this path. So now this is going to be greater or equal than it, if this is another element, meaning it's not psi naught, then this is strictly greater than E naught. So what am I saying? That if I compute the expectation value of the Hamiltonian on any state, any point of the Hilbert space, just any point that is not the ground state of the Hamiltonian, I will find an expectation value that is strictly larger than the ground state of the Hamiltonian. I mean, it looks like a trivial statement, because by definition, it's the ground state, so it's the lowest eigenstate of the Hamiltonian. So it's clearly, if I compute these expectation values to other eigenstates of the Hamiltonian, this is going to be larger than the ground state, by simple definition. The non-trivial part of this statement, however, is that psi is not requested to be an eigenstate of the Hamiltonian. So let me just put it as a note. In general, psi may not be an eigenstate of H. So even if psi is not an eigenstate of H, the expectation value of the Hamiltonian over this arbitrary state psi, and if it's not an eigenstate, I can always compute the expectation value. Of course, the expectation value of this state will have a, there will be an expectation value, but there will be a significant width of the distribution associated to this expectation value. Stated differently, if I have my system in the state psi, and psi is not an eigenstate of the Hamiltonian, if I perform the measurements many times, I will get different results every time. So what the expectation values give me for a state psi that is not an eigenstate of the Hamiltonian is just the average value of the energy in that state. And this average will be always greater than the exact ground state of the Hamiltonian. Well, that's the state. So why should this be of any interest for me for the problem solving the problem solving for the ground state? Well, because one can leverage of this, variational methods, leverage on this to find the best approximation to the ground state. So what do I mean? That if I take a state psi, suppose I have two trial states. Let me call it psi 1 and psi 2. Neither of these two states is an eigenstate of the Hamiltonian. So, if phi n is the exact set of eigenstates of the Hamiltonian, let's suppose that, phi n psi 1 is basically different from 1 for all n, and the same happens with 2. If phi n was one of the eigenstates, if psi 1 was one of the eigenstates of the Hamiltonian, then this would be equal to 1 when n is the corresponding eigenstate, right? For instance, if psi 1 was the ground state, then this would be the ground state. Okay, we can even remove and be very general. Let's suppose that psi 1 and psi 1, neither psi 1 or psi 2 is the ground state of the Hamiltonian. Right. So however, if the expectation E1 defined as the expectation value of psi 1 on the Hamiltonian divided by the norm, and I will, from this point on, disregard the norm, assuming that the states are normalized, and I do the same with E2, psi 2 H, psi 2 over psi 2, psi 2. Now, if E1 is lower than E2, then psi 0, 1 is going to be in modulus greater than psi 0, psi 2. So in other words, I get a wave function that has a larger overlap with the ground state, with the exact ground state, which means is a better approximation of the ground state. This is, if you want, the second part of the statement, of the unproved statement. So, summarizing, by finding a trial function that has a lowest energy expectation value, I find a better approximation to the ground. And the corresponding energy would be an upper bound for the energy ground states, the ground state energy. So let me write this. By finding by finding functions, states with lower and lower energy expectation value, one finds better and better approximations to the exact ground state wave function or state, ground state, and corresponding energy. So let me state it again. If I can, we all make let me state it as a sort of an example. Let's suppose I give an Hamiltonian and ask everybody in the audience to come up with their personal guess of what this wave function would be, without making any particular calculation. Just looking at the system, by looking at the shape of the potential. I ask you, can you guess a function that might be a good approximation for the wave for the ground state? And typically, whenever you see potential be very small, you would put a wave function that is very large in the point, because we expect the particle to be most of the time in low energy regions, low potential energy regions. So then how do we know who's gotten closer among us, among the people doing the competition? Well, there is a clean answer to this. Let's everyone compute the expectation value of our wave function on the same Hamiltonian. And whoever gets the lowest energy value wins, because you get the best approximation of the ground state energy and the best approximation of the ground state wave function all together. Now, for a certain period, I was collaborating with Professor John Nagley at MIT, famous theoretical physics and nuclear many-body problem solver, and later also lattice field theory expert. And he was telling me that in MIT, he used to run a competition among the students of his quantum mechanics course. And at the end of the year, he would provide the system with a Hamiltonian, sufficiently complicated. And everybody in the class was asked to come up with their own variational estimates using certain criteria that I will elaborate a little bit later, considering the number of parameters. We'll see. And whoever got the lowest energy was the winner of the competition, and he was awarded a collection of Feynman books for lectures in physics. So I think that explains quite well the principle, the variational principle of why it is useful. So how do we put it in action? How does it work in practice? So typically, a way to make it work is to, step one, make a variational ansatz. So what is the variational ansatz? Well, you take the you guess a wave function psi, which of course would be the projection of my state psi on position plate, and you make it dependent of, you guess a function of form, and you let the function of form depend on a set of parameter alpha. Alpha in general will be a set of parameters, let's say A1, AN. For example, suppose we are interested in a potential in Hamiltonian for one-dimensional Schrödinger equation, for simplicity, with a potential that is an harmonic potential, or with some correction, or even a quartic potential. Let's say alpha x to the fourth. Since alpha x to the fourth is not x to the square, we don't have a simple analytic solution for that, right? So my guess might be, for the simplest possible case, a Gaussian. So let me say 1 over root of 4. Then I'm going to work out on the, or let me call it alpha. I'm going to work out the normalization. So let's leave the normalization floating for a moment. And then let's say the usual Gaussian. Now, this Gaussian comes from noting that quartic potential is qualitatively similar to a quadratic potential, but it grows faster. But in both cases, I would expect, my wave function, my ground state wave function, to be mostly concentrated in the middle. And by the same argument that led us to guess to the Gaussian, we might be tempted to perform this guess. However, we already know that psi of alpha cannot be the exact answer, because we know that this is the exact answer for the harmonic oscillator, not for the quartic potential. And in general, it's quite easy to show that we have different potentials. In general, the answer is different. The ground state cannot be the ground state of both potentials, since these Hamiltonians don't commute with each other. Okay, so step 1, make a variational ansatz. For instance, a Gaussian. I know it's not going to be right, and most of the time I will be in this situation basically all the time. And if I knew already that I was right, that it would be much simpler. Most of the time I'm guessing a function that I'm just, capture some qualitative insight I might have by just looking at the potential. So this is really heuristically postulated. Okay, that's step number 1. Step number 2 is compute the expectation value. Now, this will, of course, depend on the specific value of the parameter that I've been using, alpha, determining how steep is the Gaussian. Trivially, because the steeper is the Gaussian, the larger is the derivative of the function, and therefore the larger is the kinetic energy, for instance. The broader is the Gaussian, the larger is the expectation value of the potential energy. So clearly, there's going to be some compromise between being steep and being broad, and the compromise will depend on the specific problem we're left in. So let's compute this. So let's once again write the potential energy landscape in the following way. Sorry, there's a second derivative here. So, and then let's say they call it lambda x to the fourth. This is the so-called coupling constant, which is there to ensure the dimensionality of the problem. So I'm gonna use any program that yields the computer to solve to solve this problem. And in particular, I use Mathematica to do the integrals. So let me be very, very pedantic. So let's say this is dx. So it's going to be e to the minus alpha x squared. Then I have a negative h bar over 2m d by dx squared plus lambda x fourth e to the negative alpha x squared divided by d by dx e to the negative 2 alpha x squared. Okay, so I'm just applying this equation here explicitly. Now, let me continue with this. So let me make some room. This is step 2. And this is the evaluation of E alpha. And E alpha will be the, there will be basically two terms. The term coming from the kinetic energy and the term coming from the potential energy. So, and the normalization. So I'm gonna write this term is gonna be C alpha, the kinetic energy, C alpha, plus C alpha, the potential energy, and the normalization. Now, let me do this stepwise. So let me, I'm gonna pause the video for a second while I compute these objects using Mathematica. Okay, so I've done my calculations. So let me tell you what is the result of performing this integral. You can check this using any computer algebra code. So I'm gonna use different colors for different terms. So let's say this, this, and this. So I have, of course, a sign here. So let's first look at what is the result of the first term, and it's going to be root of alpha h bar squared divided by 2 mass, and then root of pi over 2. So first of all, we have a very simple finding. The kinetic energies contributes to the energy in a positive defined manner. And that's not particularly surprising because the kinetic energy is a positive definite quantity. And I expect the same to happen with the potential too, because this potential is positive definite. So, so no big surprise there. So now let's look at the potential energy. The potential energy is going to be plus. The potential energy is going to be up to the normalization is going to be 3 lambda divided by 16 alpha to the 5/2, and again root of pi over 2. And the norm is trivially root of pi over 2 alpha to the minus 1/2. So say I can use same notation. So this is alpha to the minus 5/2. And so I can use this and say that this is actually alpha to the 1/2. So in other words, this allows you to perform simple simplifications. First of all, you can disregard all this. And then, of course, you can multiply everything by the denominator in the numerator, which basically leads to removing this. And of course, you have to add minus 5/2 plus 1/2. So you're going to say minus 5/2 plus 1/2 is equal to minus 5 plus 1 divided by 2 is minus 4 divided by 2 is actually minus 2. So here we can get minus 2. Okay? So in the end, when you combine all these things together, you find your result, which is not particularly inspiring. And it is 3/16. Now let's order this in the right order. It's going to be alpha h bar squared over 2m, that's this part here, plus 3/16 alpha squared lambda, and that's it. Now, I just want to emphasize that, as expected, the energy, the expectation value of the Hamiltonian, depends on the specific choice of my parameter. So I get a different, of course, if I use a different wave function, because changing this parameter effectively changes the shape of the wave function. So in the end, changes the wave function. So if I use different wave function, I get a different result. So step 3, find the best among all of these possible answers within the variational answers we have made. So we are not looking for the best possible answer in general. We are looking for the best possible answer restricted to the space of function we defined as our trial ansatz. So step 3, what we need to do is to look for the minimum of the energy as a function of the parameter. Find the optimal parameter. Find the optimal value for alpha. And how do we do that? We find the minimum of the energy by taking a derivative with respect to alpha of this result and let it be equal to 0. So if I do that, let me do that for a moment. While I do it, let my pen recharge. So I take the derivative of this guy with respect to alpha, and I solve it for alpha equals 0. And it turns out that there are 3 solutions, as they should, because this is, of course, a third order equations, polynomial. Well, it turns out that this results in a third order polynomial equation. However, 2 of these solutions are either imaginary or negative, and this doesn't work for us. And the only really workable solution is going to be the one that I'm going to write down for you, and it's one in which alpha is equal to some particular value, let me call it alpha bar, and it's going to be 3 to the 1/2, sorry, 3 to the 1/3, lambda to the 1/3, mass to the 1/3, divided by 2 to the 1/3, so we could say 3/4 to the 1/3, and h bar squared third, so in other words, 3/4 lambda mass h bar squared to the 1/3. So what are we learning here is that if we choose alpha to be precisely this value, depending, of course, of the value of lambda and m and h bar, then h bar is given by nature, but lambda and m is given by the specific system under consideration. But among all the possible wave functions in the Gaussian form, this one is the one with the lowest energy. So this one provides the best possible approximation of the original exact ground state of the problem. So in a cartoon, so let me say this is a cartoon. It's not a real calculation. Suppose I have my potential. It's very steep because it's quartic. Okay, so let's suppose this is the exact wave function, which we don't know. Well, we could get it numerically for this simple problem, and it would be interesting to look at the comparison between the exact and the variational estimates. Well, actually, we can do that. But let me, before we do that, let me just illustrate with respect. We have a number of Gaussians, trial wave functions. Now, Gaussian, I expect the Gaussian to decay is lower than the exact wave function because they travel, the tails will travel in regions where the potential energy is smaller for a Gaussian, for a harmonic oscillator, than it is for a quartic potential. So the energy penalty of traveling, say, under the shadow of the potential energy will be higher if you're in a quartic potential than it would be if you're in a quadratic potential, because the quadratic potential sort of goes a little bit slower. It's my 1/2 and the square, right? Now, among all the Gaussians, however, there is one optimal Gaussian that I will draw with purple. And this is clearly suboptimal. And this optimal Gaussian will provide my best Gaussian approximation of the underlying exact solution. Now, clearly the Gaussian guess is just a guess for this specific problem. In general, we don't have to be restricted to Gaussian ansatz, obviously. It can be any ansatz and not necessarily an ansatz depending on the single parameter. We can have more parameters, and the more parameter we need to solve, then of course the condition of optimal will be a gradient with respect to all parameters. So if my wave function's psi depends not just on one parameter, but say on a collection of parameters, alpha n, then all I have to do is to take the corresponding expectation value for the energy and differentiate it to each of these and solve a set of equations to find the optimal set of parameters. So we can use any answer that we want with any number of parameters. Of course, as we increase the number of parameters and make the answers more and more complicated, finding the parameters becomes more and more challenging, to a point that perhaps you will reach a turning point in which, you know, the computational gain of solving this problem this way becomes comparable to that of competing methods, perhaps the ones that we already discussed, and then the methods that stops being the trade-off between being practical and being accurate stops being favorable. So as a final application, I'd like to look at the problem, you know, to check how the solutions look in a particular case. So we look at a numerical example. So we look at the potential U to be, you know, lambda x4, and let's put all numbers to be simple. Let's do m equal 1, lambda equal 1, h bar equal 1, and the last one goes, that's it, because there's no more parameter in the problem. So if this is the case, our variational answers would be, so let's do, so let's say lambda equal 1, mass equal 1, h bar equal 1, and then if I look at what is this particular combination for alpha bar, it's going to be 3/2. It's going to be 3/2 to the 1/3. And if I look at the corresponding energy, so I call alpha equals to this value. And if I compute the corresponding energy, the energy looks, and the energy becomes 3/4 times 3/2 to the 1/3. Okay. That's what it is. Now, the challenge is now, can we compare this variational solution with a solution that we can get from numerical diagonalization? So to do that, we open our code for solving the Schrödinger equation. We go down here. We probably don't need to go from -6 to 6 for this problem. Let's go from -4 to 4. And we get all the parameters to 1. But this time, we don't even have this. We are going simply to say this is lambda, but lambda is 1, x ri to the 4th. Right. So if I now look at the solution for the ground state only, the ground state is 0.66. So if I look at how much this is in numbers, it must be greater than that. And in fact, if you dial in number, you can check this is 0.68. And clearly, we have gotten very close, but not quite there. So I got like 0.68, slightly bigger, 0.66, which means that this is the exact ground state, or at least the exact ground state estimated numerically with the scheme. And this is my variational calculation of the energy of the ground state. And it's almost right, just slightly above. And we can look at the we can look at the eigenfunctions. So you use new plot, for instance. Okay, so again, I don't remember quite what was the eigenvectors. Okay. Eigenvectors using 1 and 2. That's the exact solution. And it looks almost like a Gaussian, you see, but we're going to discover this is not exactly a Gaussian, because now we're going to plot the Gaussian ansatz. So f of x, that's my, let's call it psi of x, my ansatz, is going to be the normalization, and the normalization is, let me write it in numbers. It's 1 over root of 1.31. I'm plugging in numbers. Okay. And then we multiply by exp negative x squared times, and the parameter alpha. And numerically, alpha is actually alpha bar is 0.91. So now I'm going to plot this together with the other. Okay, something is really wrong here. What can go so wrong? What have I done wrong here? Oh, yeah. I was plotting too many things together. So eigenvectors using 1 and 2 side of x. And say set, and let's give it a range from -1 from -1.5 to 1.3. Okay, something is really bad here. So run again. Okay, so if there's no point to plot anything beyond -0.2. Okay, so set y range 2. Okay, so that's my wave function. That's the exact wave function. So let's go from -2 and 2, maybe. Better than this. Okay, that's my exact wave function. And the wide range is probably 2. Let's say to do this. Okay. Okay, and maybe really can do this even better. Visualize things a little bit better. Okay, now we can plot. Now the normalization of this function is completely off because probably the vectors that we were using were not normalized. The vectors that the code gives back are not necessarily normalized. So let's divide this by, say, okay, maybe. Okay, now this is, oh, we were quite lucky. So this is actually interesting because it shows us the comparison between the exact and the approximate solution. So the exact solution here is the purple dots. And as I was anticipating, if you look at the tails, the variational ansatz, which is the green line, extends a little bit further into the tails than does the exact solution, because again, this is a region where the potential energy is very high, so you pay a lot of penalty to have a finite probability to find a particle at this high value of potential energy. Of course, to have the same normalization, the value in the middle of the valley must be larger. So these little tiny differences between the exact solution and the approximate solutions are reflected by the fact that my energy is only wrong by 4%, roughly speaking. 0.2 over 0.6 is roughly speaking 4%. So you see, with a very simple answer, one parameter, naive guess, we can get already quite close to the exact result, demonstrating the power of the variational approximation, which we will be using over and over. So what is the drawback of the variational approximation? Well, one important drawback that one should always consider is that the variational approximation only is applicable to the ground state. There's no variation theorem for excited states. There is no variation theorem for excited states. So if you're interested in excited states, you have to look somewhere else. And unfortunately, many of the methods that are most efficient cannot, they are not equivalently efficient for excited states, or are not applicable to excited states. So this is a limitation that variational approximations share with other methods. The other main limitation of the variational approximation is, in fact, the fact that you need to know a little bit about the solution before you can use a variational approximation. Variational approximation is no good, no useful if you have no clue about the solution. Because you see, we already guessed the solution was sort of a Gaussian, and so we could make a very good variational ansatz. Had we tried a different ansatz, we would have gotten much worse, perhaps. So the fact that we sort of could guess the solution based in this case simply by looking at potential was a great help of finding a decent result. In many cases, especially in high-dimensional situations where you cannot simply draw the potential, maybe you have a potential, you have 6 coordinates because you have 2 particles. You cannot draw a potential in a 6-dimensional figure and try to figure out where the potential is larger and put the Gaussian there. So in many cases, physical intuition doesn't guide you very well. Well, in those cases, then of course, variational approximation become more difficult to be applicable. But there have been attempts, and I will cover some of them in the rest of the second part of the course. So with tomorrow's lectures, Wednesday the 24th, we're going to wrap up this first module and look forward to more concrete problems in the second part of the course. Okay, that's it for now. Thank you. See you tomorrow.